I told you that we don't have really a good fundamental theory of physics to discuss physics above the electroweak scale. We have ambiguities. We think there is a gut at 10 to the 15 GeV, but there might be other physics we don't understand at higher energies. One of the constraints, one of the ways to learn about high-energy physics, ironically, is to look at cosmology. We spoke about the fact that the details of Big Bang nucleosynthesis constrain modifications of the Standard Model. I'd like to discuss now a solution to some of the puzzles that I brought up in the previous clip and explain how this is being used both to resolve issues in cosmology and to apply insight from cosmology to understanding what physics beyond the Standard Model might be. And the idea is cosmological inflation. So what is inflationary cosmology? Well, inflation is an idea attributed to Alan Guth, who proposed the model in 1980. It is probably a fact that Soviet physicist called Starobinsky had come up with the idea earlier, but since at the time communication between West and East was limited, Guth did come up with the same idea independently, and it's broadly attributed to him. What is the idea? Imagine, says Guth, that at early times, on the order of 10 to the minus 36 seconds, so in his original plan, this would have happened in conjunction or in the process of the electroweak transition. We have more recent models push it farther back to prior to the electroweak transition. Imagine that the universe, for some reason, developed a cosmological term. And we know that if the universe developed a very large cosmological term, so large that it dominated the matter and radiation density, high though they were at the time. So before radiation domination, you would have a phase that was dominated by a cosmological constant. Well, if you had a time that was dominated by a cosmological constant, we know what happens in a lambda-dominated universe. A lambda-dominated universe undergoes exponential expansion. The Hubble constant remains constant, time-independent, and the scale factor grows exponentially. Now imagine that this exponential growth went on for some period of time. It doesn't need to be very large because the cosmological constant is huge, but so you have some large cosmological constant, h, which means that its inverse is a short time, and you need ht to be of the order of, say, 60. So the universe, the scale factor grows by a factor of e to the 60, some huge number. Now remember that during cosmological expansion, during exponential expansion, your event horizon shrinks. And so what is going on is that during that expansion, there are regions that previously were causally connected that are becoming disconnected. Aha. What one finds is that our entire visible universe today, everything we see, all the way back to the Big Bang, the full 46 billion light-year radius around us, all the way back to the Big Bang, is a region that before exponential expansion was well inside some pre-inflation horizon, because remember what exponential expansion does is it throws things outside the horizon. Now, if this is true, if the entire observable universe was inside the horizon prior to inflation, this answers the horizon problem. What it means is that our entire universe and the whole region around it was causally connected because it was inside the horizon and then was inflated outside the horizon. So the observable universe was a tiny part of some larger universe that got large through exponential expansion. And then, remember, in exponential expansion, things fall out of causal contact. And then as our universe expands, slowly things fall in. So we are, for the first time, seeing things at a distance of 46 billion light years, but it's not really for the first time. Way back at 10 to the minus 36 seconds after the Big Bang, we had already seen them, lost them, and now we're seeing them again. Since we'd already seen them, the horizon problem is not an issue. You understand why it is that there was such exquisite thermal equilibrium, because it had equilibrated. Okay, that solves the horizon problem. The other thing that exponential inflation does is it naturally drives omega to 1. Remember, our problem was that you had to have omega exquisitely fine-tuned to 1. How do we see that? Well, you can see this again from the energy equation, which told us that h squared times omega minus 1 is given by the curvature term, and this is the first of Friedmann's equations in any universe. I'm now not making any assumptions about what dominates the energy density. But if the energy density is dominated by a cosmological term, then h is a constant. Remember, the Hubble constant is constant with time in an exponential expansion. It does not change with time. What this means is that as a grows very large by a factor of e to the 60, this denominator grows by a factor of e to the 120, and therefore, since this is a constant, omega is driven by a factor of e to the 120 back to 1. So this exquisite fine-tuning. Why is our universe so flat? Basically because inflation flattened it. Inflation expanded some existing curvature and spread it out over this huge area so that our whole universe is a small patch of what used to be part of some more reasonable R0-sized patch, and therefore we see a very flat universe in a very natural way. So inflation answers that question very naturally. The other thing that the inflation makes clear is, since inflation happened after the gut transition, any relics of the gut transition had some constant density that we can predict from our theory of guts. And then the universe expanded by a factor of e to the 60, and the relics were diluted by a factor of e to the 180. Roughly, there is now one monopole for every horizon. So there is one monopole somewhere in a ball of radius 46 billion light years around us, and if we haven't detected it, not too surprising. So inflation in many ways is a magic bullet. It's a solution to 3 of my 5 puzzles. A wonderful idea, but it has its own question. If the universe were dominated by a cosmological constant, we said, like our universe is, then as you move into the future and A grows and radiation and dust are diluted, the cosmological constant is not diluted. It will only become more and more dominated by a cosmological term. Yet our universe has to somehow transition from being dominated by a cosmological term to being dominated by radiation, so that the processes of the Big Bang, as we can see them from here, looking back, will take over. So the question that Guth is faced with is how to turn the cosmological term on and off. Well, we had this idea of the cosmological term is the energy density of the vacuum. And Guth's original idea was that if in the electroweak transition the Higgs field settles at it away from the minimum of its potential, so there is some energy density in the Higgs field being in what is called the false vacuum, a metastable state at the top of the potential. So this means that as a function of the Higgs field, the energy density of the universe looks something like this, though you should imagine rotating this about this axis and then about another axis that is impossible to draw. Basically, the minimum here is, if you rotated this, the minimum would be a circle, and if you rotated it enough to get a 3-sphere, then that would describe our actual Higgs field. But those are details. The idea is that if, for some reason, the universe supercools so that the Higgs field is stuck here, then this measures the energy density, and of course the universe won't stay here. Eventually some fluctuation will cause the universe to roll down. This potential graph can be usefully thought of as a roller coaster. There's some friction associated, effective friction associated to the expansion, so there's a friction involved. And the idea is that the universe has a non-zero energy density associated to the Higgs field being in the false vacuum, and then this is sort of an ICE-9 scenario. The universe decays to the true vacuum, and in the process, all of this energy density gets thermalized. This field goes wiggling around here, producing lots of particles. The wiggles of this field, since they produce lots of Higgs bosons, which then decay to whatever Higgs bosons decay to. Remember, fluctuations of this field are the Higgs boson. And Higgs bosons decay to everything, and this is what populates the universe with dust and radiation and whatever we find. So this is a great idea. It turns out that this particular model, the electroweak Higgs boson as what is called the inflaton, the field that triggers inflation, has all kinds of problems. In particular, you don't actually convert the vacuum energy efficiently to radiation and matter, and so Guth had to modify his theory a little bit. This is so-called old inflation. We then have a new inflation model in which the potential looks a little bit different, very similar. This is typically thought to have occurred prior, so this potential is not for the Higgs field, but for some other field. It has to be a scalar field, so that giving it a value doesn't involve, if you gave the electric field a value everywhere in space, you'd have to, for homogeneity, it'd have to be the same value, but the value for the electric field has a direction, so that would ruin isotropy. So this is a field, like the Higgs field, a scalar field that can have an expectation value without violating isotropy. So now the field is again trapped at the maximum, but now the properties of this potential are such that it doesn't actually fall or tunnel down, but slowly rolls down over a long period of time, coming eventually to rest at the bottom, having through friction converted its energy to fluctuations. Now, and then you get very heavily damped oscillations at the bottom. This version of new inflation is an improvement, and it leads to an even more exciting possibility called chaotic or eternal inflation, to which I'll turn in a moment. I should point out that there's an interesting aspect of this that you might miss. So imagine this state, of course, is unstable. The universe is stuck in this state, and it's unstable because there's a lower energy state. So quantum fluctuations will lead bits of the universe to start at their own time, if they're causally disconnected, sliding down towards the minimum. Now, because this is unstable, there's some half-life. You'd expect that after the half-life, about half the universe would be in this vacuum, and half of the universe would be in that vacuum, and you'd be right in some sense. But remember that the half of the universe that hasn't decayed yet is still exponentially inflating, whereas the half that is not is at best power law, square root of t, expanding, because the energy has been converted to radiation. What this means is that in terms of the volume of space, there's still almost all the volume is in the false vacuum. So even the new inflation is in some sense eternal, and I'll explain what I mean by that, in the sense that most of space is still inflating. We just happen to live in the region that has decayed. This led primarily a theorist called André Linde to propose a model that he called chaotic inflation, and we now know by the name eternal inflation. There are various versions of it. Here, you don't even need a phase transition. All you need, he realized, is a potential of some form such that the expectation value, some physical parameter, rolls slowly down it. And then you, for some reason, have to create a universe with a non-zero energy density for this field. And so in other words, this field is away from its minimum. And then the field will naturally, if you set the parameters right, roll slowly down. What that means is different regions in the universe will slowly roll down through a quantum fluctuation. If you have different vacua and quantum fluctuations lead one region of the universe to roll down, then again what you notice is the majority of the universe is still inflating. In fact, from the point of view of the exponentially growing universe and the co-moving coordinates of the exponentially inflating universe, what has happened is that some small region decided to decay to a smaller, less rapid expansion, and now its size is only growing like a power law, whereas distances in the exponentially inflating universe are growing exponentially. So basically this effectively pinches off, and the inflating universe goes on completely unaltered. And so you can imagine a situation where you have an eternally inflating universe. Remember that an exponential growth does not have the same finite time in the past singularity of the Big Bang that does a power law. So you can imagine a universe that is and always has been exponentially growing. And at various times, at various places, through a quantum fluctuation, the field transitions from a value with a high energy density to a value with a lower energy density. And when it transitions to a value with a lower energy density, that region first gets filled with radiation and matter as the field rolls around at the bottom of the potential well and converts its energy to radiation and matter. And second, starts expanding very slowly, relatively, by a power law. This is our Big Bang. Our Big Bang was really seceding from an exponentially expanding universe. Now we are left with a non-zero cosmological constant, a very small one. So here you can be left with a very small cosmological constant. The minimum of this need not be zero. This is all great. Once you get the idea of this sort of eternal or chaotic inflation, one understands that, okay, now you can have a situation where there are many stationary points of the potential with varying values of the cosmological constant, of the vacuum energy density, and as regions of the universe fluctuate between them from higher to lower values, this releases energy to convert into radiation and matter, and all of these regions pinch off as what's called baby universes. Guth called this the ultimate free lunch. The big universe continues to expand, and as far as it's concerned, what it's lost is an exponentially shrinking part of its volume. Whereas over here, you have a universe that begins power law, slows down to radiation-dominated expansion, and could eventually produce a universe as large as ours, if given time. So this is, and of course, this universe might have a non-zero cosmological constant, and that could decay to an even smaller value of the cosmological constant, so there could be fleas on fleas, and in this model, the sort of main branch is the highest value of the cosmological constant, main because that expands fastest, so no matter where you start, that takes over, and then everything else has branchings off of successively lower values of the cosmological constant, which to themselves look like universe, but to the expanding universes with higher cosmological constant look like fleas and immediately disappear. And so this leads, starting from an eternally expanding universe, to many sort of disconnected bits of the universe, and they're disconnected for all time. They're now completely outside each other's horizon. The entire horizon of every point in our universe becomes effectively disjoint from every point in that universe. The connection between them from both points of view becomes negligible. So there are multiple universes, in fact, an infinitude and an always growing number of various universes, all of which decay in some random way to some vacuum out of whatever the stationary points are of this potential. This can be a potential in one dimension like I drew, or in many dimensions. This is called the multiverse, and as we will see, it is an idea that has received some reinforcement from various ideas, in particular from ideas in string theory. Okay, so string theory, multiverse, causally disconnect. How am I going to... What has all this got to do with physics? If these regions are causally disconnected, we cannot see them. Is there any physics in all of this? And the answer is absolutely yes. Because this idea of eternal inflation, or certainly inflation, but in particular in the way that eternal inflation works, makes specific predictions. See, what happens is that reaching all the way back to pre-inflationary times, there are quantum fluctuations of this inflaton field. And these quantum fluctuations change the energy density of the universe by small amounts locally. And you can model the behavior of this field. It's rather universal behavior. And it turns out that this will produce what are called adiabatic fluctuations. Fluctuations in the energy density which couple equally to dark matter, to baryons, to radiation, to everybody, producing precisely the kind of fluctuations that we saw we wanted to start with, where all modes of energy density were excited equally. Furthermore, it would produce this with a characteristic spectrum of wavelengths, and what this has to do with is that quantum fluctuations in the original field are inflated until they are outside the horizon, and then they freeze in and are ready to be the seeds for density fluctuations in what becomes the radiation-dominated era. So this predicts a particular form of the spectrum for density fluctuations, which we can check against our CMB, our cosmic microwave background observations. And it is here that these predictions become meaningful on very small angular scales. It is here that the high-resolution images from the Planck mission have, to very high accuracy, verified these predictions from inflationary models. And so, while distinguishing the various flavors of inflation becomes a sophisticated problem that we are not going to address, in fact, we have very good reasons, other than the aesthetic solution to the three puzzles that I outlined, for thinking that inflation is a part of the history of the universe because of the agreement of the power spectrum of cosmic microwave background fluctuations with the predictions from inflation and with the fact that there is no other known mechanism for producing this kind of scale invariant or almost scale invariant fluctuation spectrum. Remember, we said fluctuations at all scales below the horizon. And this is indeed what inflation predicts. And so, through cosmology, we have a guide to the builder of fundamental physics models. Your model must or should be amenable to in explaining eternal inflation. You should have a scalar field with, or multiple scalar fields, with multiple vacua among which they can transition so that you can emulate this sort of eternal inflation scenario. If you do, then these various universes, which are different solutions to some big equations of motion of this big model, can have completely different values of the parameters. We said they might have different cosmological constants. It turns out that other parameters can change as you move around this model space. And so one imagines then that when one tries to understand how is it that we live in a universe where the cosmological constant is small but not zero, and yet small enough that it took 8 billion years for dark energy to dominate, long enough for stars and galaxies and stars and planets to form and even life to emerge on our planet. Somebody had to fine-tune the parameters as well as things like the strength of the relative strength of the electromagnetic coupling. One idea is maybe there are many, 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 many universes, and we happen to live in the one in which we can live. This veers from science. The sort of anthropic reasoning is on the verge of philosophy, so I'm going to stop there, but I thought I should mention that that's another way that the multiverse gets used. The more scientific version is chaotic inflation or eternal inflation explains the power law behavior of the spectrum of cosmic microwave fluctuations, as well as resolving the horizon problem, the flatness problem, and the relic problem. Pretty good.